What's causing this effect? Does this remind you of something from the 1980s or 90s? So this is color changing, very small dots, but it's not LED. This is fiber optics. Let's talk a little bit about fiber optics and specifically about Snell's law and how that helps describe the way that light travels through different surfaces. Let's take a look at what's happening inside. So here we have the illuminator in a fiber optic. In this case, this happens to be a halogen MR16 lamp, but they make these in LED as well. There's a fan here for active cooling because usually they're trying to extend the life of these lamps as long as they can. That illuminator is pushing the light through to this color wheel, and the color wheel is what actually is transforming the overall color of light. I'm going to take out the wheel for a moment just so you can see. This is the overall white light that you would get from the illuminator, but it's fun to look at it with color, so we'll keep that. The color is exiting through from the illuminator into these big, thick chunks. This is all fiber optic cables bundled together. The illuminator has provided a very focused forward direction of the beam, and that is what is pushing through these strands. Each of these fiber optic strands, fiber optic can either be made of glass or of PVC, different plastic types. It's very important that you understand the bend radius that fiber optic can accommodate. First off, why would we use fiber optic? So, fiber optic is a great way to remote the light source itself from the thing you want to light. We tended to see it a lot in things like pools and fountains where you don't want to have to empty out a pool or stop the fountain in order to access the lighting. Instead, oftentimes there's an external illuminator running the color or running the light through these fiber optic channels. That way you could light up the fountain while the actual electrical components and the actual light fixture part of it were remoted to an access panel somewhere else. We don't see it used as often now because LED solves a lot of those issues, that it has fairly long life, so the idea of access is not as important if it's going to last 100,000 hours. The other thing is fiber optic is not very efficient, that over the distance of these light pipes, we're essentially losing based on the inverse square law. So over the distance squared, the light level is decreasing. Let's take a look at some of these specific strands and understand how exactly Snell's law is working. So I'm pulling out a couple of these fiber optics to really look at the end of a strand. The light is passing through from the illuminator all the way through to these pipes, and the reason we see this glow of light at the end is really because of the geometry of the fiber optic cable. That as light is traveling through the cable, it's rebounding off those walls, but the density of this material means that unless the light hits at an oblique angle, it's going to continue to reflect internally. It's called total internal reflection. So in this portion, there's no light exiting this part of the fiber because there's no light hitting it at a hard angle. Instead, it continues to funnel down the pipe. If I start to bend one of these sections, you'll see light collecting, and it'll become more and more noticeable. I'm going to actually pinch this one, and now we've got this tight turn in the fiber optic cable goes tighter than the Snell's law will allow. So instead of total internal reflection keeping the light in the pipe, some of it is starting to rebound out at this point because of the angle of incidence. And we'll see now that I've done that, we have more light rebounding in odd ways along this particular strand. I'm going to bundle these for a second. And you can really start to see a general glow to these. There are different types of fiber optic. These are end illuminated, but you can also have end emitting fiber optics. You can also have side emitting fiber optics, which means the light intentionally comes through the sides. I've kind of created my own side emitting fiber optic with this portion here. because we've distressed the fiber optic edges enough that it's almost as if it's got a little lens to it, and that can create more of a side emitting. I've done this with a longer segment here, and you'll see that if we compare an end emitting fiber optic with a side emitting fiber optic, the end emitting fiber optic is much brighter. There's a lot more light coming out of it. The side emitting fiber optic is more muted in its tone. So again, fiber optic is still used, especially for areas where we either don't have easy access above a ceiling or behind a glass panel or underneath the water. Or it could be used when we really want a narrow, small effect. Going back to how this was applied for this particular sign, if the goal here was to create the NICID logo with tiny dots, this would be very hard to do with LED. Possible, but harder to do. With fiber optic, it becomes a much easier endeavor because each point can be so small. We do sometimes see this technique used for star ceilings as well.